All right, so one of the other requests was to talk about special numbers like e and pi. And again, as I said earlier, I don't really care what you ask me to talk about. I will use it to talk about what I want. So, but I will humor you along the way. And so I will eventually get to the unit I was going to do, but I will start off by talking a little bit about e and pi, calculus, and I will lead to my favorite calculus problem. It uses almost every idea from Calc 1 to correctly solve it. And so this is the one problem does all. It starts at a level that is appropriate, I think, for elementary school kids, and it can quickly become very difficult. If I had fully prepared, and not just preparing as I was driving in, I would have taken one of my daughter's books. Does anybody know Click, Clack, Moo, Cows That Type? I often use that when I teach this unit. Okay, so here's the question. E to the pi, pi to the e.
I think you've lost elementary school kids already.
So this part I'm not expecting the elementary school kids to know. But which one do you think is larger? Pi to the e. They're going to be close, right? And so, one of the reasons they're close is e and pi are not that far apart. E is about 2.718, pi is about 3.14. So which would you rather have, a larger base or a larger exponent? All right. All right, and so the first one, e to the pi, is about 23.14. About. I won't give you all the digits. And the other one, pi to the e, is about 22.46 if you round, I think. Yeah. All right. So at this point, it's not that hard, right? I think at this point, we can all see it goes like this. So the question is, how can we do this without using a calculator? What does it even mean to raise e to the pi? So this is where you can go all the way back down to, if you're dealing with college students, high school students, they can manipulate these things very well. If you ask them, what's the derivative of x squared? 2x. What's the derivative of x to the 5/3? 5/3 x to the 5/3 minus 1. What's the derivative of x to the root 2? Root 2x to the root 2 minus 1. They can parrot this back. But if you ask them, what does it mean to raise something to the root 2th power? Complete, I don't know. We'll take my calculator and just plug it in. And you're just formally manipulating things without knowing why you're manipulating them. So in terms of something like this, they can plug it into the calculator. But if you said, how would you actually compute what e to the pi is? What does it mean to raise a number? Really, the only way we know how to do something is, e to the x is 1 plus x squared over 2 factorial plus dot, 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 dot. And this is the infinite series expansion for the exponential. There's a lot of stuff that can be said about this. I'm not going to go into too much detail. I don't want to revolt. There's already a storm coming. There's a great excuse people could use. Oh, I'd love to hear more about this infinite series, Steve, but storm is coming. So this is the definition of e to the x. It's a really good definition. It turns out e to the x times e to the y is e to the x plus y. I might have talked to some people about this at the end of class last time. You can prove every trig identity from this. And if I give you something else, if I give you b to the x, I want to write this as e to the w. Well, if I take the log of both sides, in college we always use log for log. I'll use ln for natural log. The natural log of b to the x is the natural log of e to the w, which is just w. So w is the natural log of b to the x, which is just x times the natural log of b. So this b to the x is the same as e to the x times the natural log of b. This is now just multiplication, and now you plug that into the infinite series expansion. So we have at least a way to interpret what any number to any other number means. It's a little strange that you have to do this. If you want to prove calculus rigorously, if you want to actually calculate what is x to the root 2's derivative, you would actually have to go through an argument like this. It's very different than the argument you would use to calculate the derivative of x squared, x cubed, or even x to the 5/3. Those can be done using the binomial theorem. All right, so this at least gives us an idea of what we mean by this. What I want to talk about now is how we can actually compare them without using all the stuff like this. It's going to illustrate some key ideas from calculus, which we'll then use for another problem, which has some interesting applications. So one of the hardest things in mathematics is to take a problem that you're given and find an equivalent problem to it where the algebra is easier. So if I'm trying to compare these two things, it turns out I can more generally look at e to the x versus x to the e. And just vary x and just see which one is larger. Ideally, one of them would always be larger for every value of x, and then it would be very easy to put in the assignment, just take x equals pi, it's always greater. So let me try to compare e to the x versus x to the e. Okay, so I want to just compare these two functions, and I want to get a sense of how would I compare two functions and look at growth rates. Well, one thing I could do is I could look at f of x is e to the x minus x to the e. And if I want to see how a function changes, I look at its derivative. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. And so if I look at f prime of x, I would get e to the x minus e x to the e minus 1. Sometimes it's easier to look at a related function. And what I tell my students is every now and then in mathematics, you have to have Pavlovian responses. You just automatically do something. And my students know whenever they see a product in one of my classes, they immediately take, I'm sorry? Not factors. We don't know how to multiply things well. We know how to do what? We know how to sum. How can I get from products to sums? Logs. And so my students know whenever they see a product, they immediately take logarithms. So I should really view this e to the x and x to the e's as products. So what I'm going to do is I'm going to look at the natural log of e to the x versus the natural log of x to the e. Because if I can figure out if the logs are greater, then I know if the original functions are greater. The log is a nice one-to-one increasing function. If it's greater here, it's greater there. And the advantage of this is now I can take my function g of x is going to be the natural log of e to the x is x times the natural log of e minus e natural log of x. And what's the natural log of e? 1. So I can even erase this. Let's draw a really big minus sign. All right. Now if I take g prime of x is 1 minus the derivative of natural log is 1 over x, so minus e over x. And so the way I like to plot things in calculus is here's my function f, here's my function f prime. And I look for critical points. So here's 0. Where does the first derivative vanish? Where does g prime of x equals 0? When x equals e. So when x equals e, this is where interesting stuff happens. All right, so when x equals e, the first derivative is 0. If x is less than e, what do we know about the first derivative? The first derivative is negative if x is less than e. So my function is decreasing from 0 down to e. When x is greater than e, what do I know about my function? The first derivative is positive, my function's increasing. So I know a great deal about the shape of the graph just from this. So I want to now evaluate my function. Well, when x equals e, this is a very easy thing to evaluate. I get e minus e, which is just not 1. E minus e is 0. Right? So at e, my original function is 0. But we know the function is decreasing coming down to e. And then increasing after. So it's got to look something like this. So without going into too much detail, I know enough to sketch the curve to see that the minimum is when x equals e. At x equals e, the two functions are equal. And for any other value, the function is going to be positive. Well, the only way this can work is this has to be a greater than sign. And if that's a greater than sign, this has to be a greater than sign. So what I like about this problem is it shows you how to use some of the key ideas of calculus to get a sense of what's going on. We can get a sketch of the curve, And curve sketching is a subject that was really big when I was taking calculus and when I first started teaching calculus. Now curve sketching for the most part is forgotten. Students have calculators, students have access to programs. They don't have the ability to quickly sketch and see what's going on. I think this is a little bit of a shame. I think it's nice to be able to look at the problem and get some feel for what's going on. And here, this is what the first derivative is telling us. It's the rate of change. It's how is the function changing. If the first derivative is positive, you're increasing. If the first derivative is negative, you're decreasing. We can get a quick, rough sketch. The other thing which I really like about this problem is, if you want as a nice homework problem, try to do a similar analysis looking at this. And try to find the critical points here, and try to do all that analysis. If you take x equals e, it does look like something nice is going to happen. Are there other critical points? To me, the analysis is a little bit harder here than it is here, and this illustrates one of the reasons why we like logarithms. Logarithms make things a lot simpler to see relationships. And for my students, frequently logarithms are these magical things. If I give them, if we had written out this the long way, x times the natural log of e, what rule would my students have used to take the derivative? They'd use the product rule. They wouldn't realize that the natural log of e is just a constant. This gives rise to the log-log plots. If you have a relationship that's nonlinear, sometimes if you take the log of both variables, you end up getting a nice linear relationship. And it's a great way to present information.
Should those both say g and g prime?
Oh yeah, that's right. These should be g and g prime, not f and f prime. Thank you. G.
Then you were just saying because the log is always positive except at e.
Well, the log is, what we have is that if x is greater than y, then the natural log of x is greater than the natural log of y, and vice versa. In fact, these two statements are equivalent for x and y greater than 0. The ordering is preserved under the logarithm. So if I'm just trying to see how they're ordered. All right, so most people probably don't care about is e to the pi greater than pi to the e. Why do I care about a problem like this? It is going to be related to one of the most important problems in computer science. So what I want to do now is I want to consider the following problem. I will start off with a nice version that you can give, I think, in elementary school and start to tweak it. So you have the number 100, and you want to split into non-negative summons such that their product is maximized, such that product of terms is maximized. Okay, so I want to take the 100 senators, I want to break them up into groups, and I want to multiply the size of the groups, and I want to get as large of a product as possible. So the first thing is to look at some of the keywords. Why do I say non-negative?
You have an infinite number of summands, and when you multiply them, you'll get a negative number, so that can't be the max.
Well, so is there any way I could get a larger value by using some negative numbers?
It would be different than using the same as positives, though, right? You would have to have an even number of negatives, but that would cancel out. Right?
You can't add two negatives and get positive 100.
No, we're multiplying.
I know, but if you're splitting it into summands,
Mm-hmm.
so you can't get two numbers that add to 100 if one.
It doesn't have to be just two summons. Could be 3 numbers, could be 4 numbers.
Yeah.
So I could do negative n, positive 2n, positive 100. Right? And if I do something like that, the product is going to be arbitrarily large. So in terms of giving problems like this is, how do you have a well-founded problem? And you can decide how much you want to give to the students. You can even ask them, why are we assuming non-negative? Well, if I don't assume non-negative, I could have the product to become arbitrarily large. Okay, so this is why I say non-negative. Can you fix the word non-negative and put in a better word than non-negative? Positive, right? If one of the terms is 0, the product is going to be 0. So let's put positive. All right, so now we have positive. All right, so we're making progress. So can anybody give me any lemmas about the possible summons? Thou shalt not use
0?
Okay, so we just proved thou shalt not use 0 because it makes the product 0. Good. Anything else that should not be used? 1. Why would it be bad to use 1? It's not going to help. Right. So the first fact is no 1s used. Because if you ever had a 1, you could just fold it into something else.
I would say no numbers between 0 and 1.
Okay, so no numbers between 0 and 1.
Are we
So-
only on integers?
So that's a good question. What do you think?
We're starting with an elementary, I would say.
All right, so let's start with integers. Positive integers. And then we'll get rid of the word integers later. But let's just work with integers right now. This is something you can do with elementary school kids once they know how to multiply.
If you're using the context of Congress, I think we need to use integers, right?
Yes. I will not say, since this is being recorded, if there are or not some sentences I would like to cut in half or other divisions. But, so no 1s are used. Can anybody tell me what else we might not use? Got a lot of other numbers left. We could use 2, 3, 4, 5, all the way up to 100. Can you exclude anything else?
You can exclude 100.
We can exclude 100. Why not? Why no 100?
Then you have to use 0.
So, we could just write 100 as 100.
But then that's not the biggest you can get, obviously.
Why, obviously?
50 times 50.
Okay, 50 times 50. So 50 times 50 beats 100, so no 100.
199.
That's the slippery slope.
But instead of comparing 100 to 50 times 50, I'm going to do a little bit better comparison. Why is 50 plus 50 not necessarily the best comparison? Because when will that comparison break down? Once my number is smaller than 50. I'm going to break 100 as 98 plus 2. Which would I rather have, 98 and 2 or 100? 98 and 2. And because I have the 2 here, I'm going to be able to go very far down with this. So now, no 99 compare to 97 plus 2. And I'm going to be able to keep going for a long time like this. What about 6? Compare to 4 plus 2. 4 plus 2, their product would be 8. 8 is better than 6. What about 5? So compare to 3 plus 2. What about 4?
No, because
2 plus 2 is 4. Okay. No 4 as 2 plus 2 is as good. So I'm not trying to find all possible ways. I'm just trying to find the largest product. And what I'm saying is, if I ever had a 4, I could break the 4 into 2 at plus 2. So why not get rid of all the 4s as well? And so now I know I only have 2s and 3s. So only 2s and 3s. If I didn't take this step, I could have 2s, 3s, and 4s. That gives me more things to play with. I don't want more things to play with. I want to have the simplest possible. So now it's all down to 2s and 3s. How many people want lots of 2s? How many people want lots of 3s? Which would you rather have, 2s or 3s?
3s.
I'm sorry? Why more 3s?
When you're multiplying them.
Yeah, so the problem is you have a lot more 2s, but the 3s multiply better. So
A healthy mix.
2s. This is America. We don't do healthy mixes. We go to extremes. So how can we compare? How can we get 2s and 3s on the same scale for comparison?
But you can't just use the 3s because you'd end up at 99.
Okay, so one possibility is we can't just use the 3s. But how can we put 2s and 3s on the same scale to compare them? 6s. So every time we have 3 2's, it's equivalent to 2 3's. And what's the product here? And what's the product here? So which would you rather have? I'd rather have the 9 than the 8. So every time I have 3 2's, I can always replace it with 2 3's. So you either have 0, 1, or 2 2's. And I just have 3 cases to try. So try 0, 1, or 2. Right. And so I think it's going to be a bunch of 3's and then a 4. Yep. And then 2 2's. So you're going to end up with 32 3's and then 2 2's. But there's only 3 possibilities. No 2's. Well, if you have no 2's, it doesn't work. If you have 1 2, then it would be 98, which is not a multiple, so it doesn't work. So you've got to have 2 2's.
So you try to have a minimum
Right.
number of twos that you need.
Yes. The threes are better. Okay. So now the question is, why is this related to what I was talking about earlier with e and pi?
The third or 32nd.
So this is very similar to what we had before with the e to the pi and pi to the e. We're comparing 2 cubed versus 3 squared. Can anybody tell me the number e? What's the value of e? So here is the surprising fact. Is this still in the camera range? All right. Here's 2. Here's 3. Somebody give me a number between 2 and 3. All right, somebody give me the natch. Come on, give me 2.5. Now give me another number between 2 and 3. No. Now I want it. Now I want e. Now I want e. E is closer to 3 than it is to 2. That's why we end up with more 3's than 2's. The explanation is that e is closer to 3 than 2, that e is larger than 2.5. Why do we care about this? I'll give you a nice article that goes into more detail. We talked a little bit about base systems last time. We talked about the Babylonian base system. We talked about the base 10 system. Bases are very useful. What base do you think the universe cares about? Base E. Universe loves base E, but for human beings, base E is not necessarily the most natural one to use. Okay? In the human world, what's the natural basis to use? 10. What else? Binary. Right? Why do we like binary? Yes, our future machine overlords really like base 2. Right? On, off, yes, no, 0, 1. Base 2 is very convenient for a lot of things. There's the binary search algorithm. There are lots of great things with base 2. But there are some advantages for base 3. In terms of storing information, base 3 is actually a little bit more efficient. I'm not sure in terms of recalling the information, but in terms of just how much space it takes to store things, base 3 is more efficient than base 2, and the reason is because e is closer to 3 than it is to 2. And so in terms of talking to your students about all the different base systems and all this stuff and why we care about all this stuff, when you're building a computer, you have a lot of different things that you could be concerned about. You might be concerned about data storage. And if you're really concerned about data storage, base 3 is a little bit more efficient. Now, it's not as nice for some other things. Binary search, going through the lists, very nice in base 2. But it's sometimes nice to see other examples. And so what I'll do now is I will show how to remove the word integer and basically use everything we need to know from calculus and relate this to what we just saw before. So how many of you teach calculus? Okay, so these are some things that, it's a bit advanced, but it really ties in together so many of the different concepts we have from a calculus class. It's related to what we had before. I think it's a nice way to see how the stuff builds together and how you can get a feel for a complicated function. So we want to remove the fact that we no longer require the pieces to be integer. We did that beautiful analysis before that said we only had 2's and 3's. How much of that analysis survives? Do we have to go all the way back to the beginning? Is 50 back in the game now? No. So we know we don't have, when we break it up into just real numbers, we know we're not going to have anything larger than 4. And we know we're not going to have anything smaller than 1. So we know all the pieces are between 1 and 4. And the question is, what's the best way to do it? The difficulty is we don't know how many pieces we're dividing it into. And so what I want to show you is how to figure out how many pieces to divide it into. And then once you know how many pieces, we will then figure out the best way. Okay? So how many of you again have seen Click, Clack, Moo? Okay, it's a great children's book. It starts, Farmer Brown has a problem. All day long his cows like to type click, clack, moo, click, clack, moo, click, clack, moo. And so I bring this in when I teach calculus and I start reading it because I say, well, that's the literary one, but in mathematics, Farmer Brown has a different problem. Have any of you done the Farmer Brown problem in calculus? Farmer Brown has cows and he is obsessed with rectangles and he will not allow his cows to be in anything other than a rectangular pen. And so if he has a certain number of meters of fence, what is the maximum rectangular area Farmer Brown can enclose? Okay? And I will tie this to the earlier lecture today. Okay? So you have, say, x, or 2x plus y equals the perimeter. Okay? And you want to maximize x times y. You want to maximize the area. So it's a rectangular pen. Here's x, here's y. There's the bad cows. Okay? What is the maximum area you can give the cows?
Square.
It's a square. Why?
Half the fencing is width and half the fencing is height.
So the question is, how do you prove it's the square? Well, one thing is you can say, well, look, if I solve this, I get y equals p halves minus x. So the area, as a function of just the one variable x, is x times y, is x times p halves minus x. This is just a parabola. And if I plot it, where's the parabola 0? When x equals 0, when x equals p halves, the maximum is the midpoint at p over 4. So you don't even need calculus for this.
That's how our 8th grade book
Yeah.
introduced parabola.
Yeah. I prefer to fire cannonballs at the bad guys, but Farmer Brown is perfectly fine. So this is the Farmer Brown problem. And so what we've just shown is if you have two numbers with a given sum, the maximum product is when they're equal. You can use calculus as well. I'm trying to avoid calculus as much as possible. There's another version of this problem. I call it the Farmer Bob problem. And so in the Farmer Bob problem, it's very, very similar, except Farmer Bob lives next to a big river or an ocean. And he wants to maximize how much his cows can get. So what's the answer now?
X and y add up to half.
Okay, how do you prove that?
The maximum is when half the fencing is width and half the fencing is the length. Always.
I didn't hear what the original.
Okay, so Farmer Bob doesn't have to do one side because it's the water, and the cows won't go into the water. It's very similar, except you get one side for free. So how can Bob maximize the rectangle? So the answer is the width is twice the height. How can you quickly see this? So how do you get that that's the answer? Did you do the calculus problem?
You can do another parabola.
You can do another problem. You can do another parabola. You can graph it. You can also use lines of symmetry. This is supposed to be a well thought out, cohesive set of lectures building to, right? So that you will be so enraptured you won't even care about the feet of snow you're driving home through. So I use one of the most useless superheroes, I think. Aquaman. Okay? He can throw balls of water underneath and talk to fish. Okay? So at the same time Farmer Bob is making his rectangular pen, Aquaman is making a pen for his fish. Whatever is optimal for Farmer Bob has to be optimal for Aquaman. Right?
Got a Leviathan, you have to put it.
Here's a Leviathan, wants to give it maximum possible area. So whatever is optimal for Farmer Bob, the reflection is optimal for Aquaman. We've now doubled the amount of perimeter. What's the optimal solution? A square. So therefore, without doing any calculus, we know it has to be half the square. And so if this is 20, these would be 10. And so again, we don't need this for what we're doing, but I like it because it ties to this idea of lines of symmetry. It ties to using symmetry to help you avoid certain calculations. Okay, what we will use is the Farmer-Brown that if I have a fixed area, the best I can do, if I have a fixed sum, the best I can do is a square. Okay, any questions on what we've done so far?
If it was Rancher Bob, though, he'd know that his cows are just walking through the water and around the fence.
If the one's really steep, then how tall is the fence?
If there's a bluff, then
So I want to get into Princess Bride with the...
My mom raises cattle, so she'd be mad at me if I didn't say that.
I won't ask how old you are and that you still... No. No, my parents live in Arizona now. They retired there. They were sick and tired of the Boston weather. We actually had a snowstorm in the desert which delayed us leaving them this year, but Arizona is an open range state. And if you don't want the cattle to come into your development, you are responsible for putting up the fence. Yes, so these are important problems. So let's get back to splitting into positive integers. So let's assume split into n pieces. So we have 100 equals a1 plus a2 plus an. And what I'll do is I'm going to find the best I can do for value of n, and then I'm going to vary n. So it's going to be a two-stage process. And again, stuff like this, students often have a lot of trouble when you have multiple things going on. And so we don't know how many pieces we partition into. Let's assume we partition into 2. What's the best we can do? Let's partition into 3. What's the best we can do? Into 4, the best we can do. And for each one, we get a number of the best, and then we see which one of these is the best. So now, what can someone tell me about the A's? I'm sorry?
The A's?
Yeah.
We want them to be equal.
We want them to be equal. Why do they have to be equal?
So we can get squares.
So we can get squares. So we want to maximize the product a1, a2, ... an. Imagine two of them were not equal. So without loss of generality, let's say a1 doesn't equal a2. If a1 doesn't equal a2, let's let a1 tilde, bless you, be a1 plus a2 over 2, and a2 tilde be a1 plus a2 over 2. If I have two things that aren't equal, well, look at all things that have that as their sum. The maximum product is when they're split equally. So this can't be the best. The best has to be when a1 equals a2. Similarly, a2 has to equal a3, a3 has to equal a4. They all have to be the same. If there was ever one that wasn't the same, then I could make the product larger. In the interest of full disclosure, you then need a small result from real analysis that says there actually is a maximum that you attain, that there is something that will give you the best possible product. Hopefully that's pretty clear from something like this, that you're not going to be able to get the product arbitrarily larger, or you're not going to be converging but staying a little bit below something. Most students do not have a problem accepting the fact that there is a best thing you can do. But for this, to really do it fully accurately, you would have to say there is a maximum choice. We've just shown, using the Farmer-Brown problem, that if we split it up into n pieces, the best we can do is when they're all the same. Is there anything special about 100? Could I have done it for 101? 102? Square root of pi? So we could replace 100 with just any old number s, for our sum. And what we've just shown is that if we split s up into n pieces, each piece is equal. So we get best when each ai is equal to s divided by n. So the product is, we'll call it f of n is s divided by n raised to the nth power. And now we want to maximize over n. So as soon as you hear, I want to find a maximum, what do you think of using? The derivative. This is one of the big things in calculus. Why do we care about derivatives? Derivatives give us rate of change. We look for critical points. We look for places where the first derivative is 0. What's the problem of differentiating this function? We will have to use logs. That's actually a minor issue compared to the major issue that's lurking.
Because you have a variable raised to a variable.
Not a problem. I can write it as f of n is equal to e to the n times the natural log of s over n. And that's one of the reasons why we talked about that stuff earlier, unified lecture.
Why it's undefined when n is 0?
It's not,
Well, but
we're not letting n be 0, but you're on the right track. This function is only defined right now when n is a
Even number?
integer, close, right? We can only divide s up into an integer number of pieces, right? I'm not going to say, we're going to order 4 pies and we're going to divide them up into equal amounts so that all 7 3/4 people who are here today, get an equal amount. We can only divide things up into integer pieces. Well, calculus does not work for functions defined just on the integers. I need functions defined on the real numbers. So the solution is beautiful. The solution is basically screw it. If this wasn't being recorded, I would use stronger language and just replace every time you see an n, except in the name log, because that's with a real variable x. And now I have a function of a real variable. Can I differentiate a function of a real variable? Yes. And then the question is, how do I find the best integer from the best real? And so I'm not going to go through all the details now. What you would do is you would calculate f prime of x, and then you would have here's f, and here's f prime. You would find a certain critical point. I will leave that deliberately vague. And so you have some special critical point, we'll call it c, where the first derivative is 0. And it turns out that the function is negative. I'm sorry, I want it to be maximum, sorry. The function is positive. F prime is positive coming up to that critical point, and then negative afterwards. So what does that mean? My function has to go up, reach a maximum here, and then come down. So look at all the different concepts we're using from calculus. We're using curve sketching. This is going to be a really nice derivative to do. It involves a chain rule. It involves a product. You might want to use the log laws to simplify. So the more algebraic simplifications you do, the easier it's going to be. As not everybody here has done calculus, I will leave this as an exercise. If you want to go through, I'm happy to send notes. I believe I've got this written up somewhere as to how you would take the derivatives. But frequently we give our students cookbook problems, find this derivative. We don't care about this function. This is busy work to make sure you know the concepts. Here is an interesting busy work function that actually has meaning. And at the end of the day, we will find the maximum is at c. And that's going to be how many pieces we divide it into. And so then each piece is going to be of size s over c, or the closest to it. What do you think the value of x is going to be? Without doing the calculation based on what I've been saying. So if this point c is e, then that means each point is s divided by e. What do we think each piece should be? That could be way beyond our range of 4. What do we want each piece to be? We want each piece to be about e. So if we want each piece to be about e, we would expect n is about, so c is actually going to be s divided by e. And so without even doing the calculus, based on what we were doing before, we have some really good intuition as to what the answer should be. So there's a lot of reasons why I like this calculus problem. There's a huge amount going on here. It includes curve sketching, and this is not a standard function to sketch. But we don't need that detailed of an answer. We just need enough of a rough answer to get a sense of what's going on. It really highlights why we care about the sign of the derivative.
Does this connect to why nature divides by e so often?
It might. I mean, that would be an interesting thing to look at. I mean, I know why nature divides into Fibonacci's,
Right.
which we will get to later today. But in terms of why we divide into E, I'm not sure. But it could be coming down to maximizing certain things. And there's a lot of stuff going on here. You can talk about why we should convert to base 3 rather than base 2. Any Isaac Asimov fans here? Okay, the gods themselves, which is a really interesting story by Isaac Asimov, are in a race with, in some sense, like 3 genders that have to come together. So lots of stuff here. You can break it up into lots of smaller sub-problems. So you can show, here's a bunch of things we've looked at during the semester, and here's how they all fit together. Here's a bunch of smaller sub-problems we can do. Rather than trying to do the whole problem at first, breaking it up into an arbitrary number of pieces, try to do something simpler. Break it up into 2 pieces, 3 pieces, 4 pieces, and see what's going on. Try to look at simpler cases. In general, finding the best integer solution is not going to be easy finding the best real solution. The best integer solution could be very far away. We're lucky here, and this is the key concept of the derivative. This is the first derivative test. If the first derivative is positive on one side and negative on the other, you have a local maximum. This is a great way to see that and to say, I don't need to know that detailed of a curve sketch. If I now want to find what's the best integer maximum, well, okay, this is supposed to be s divided by e. Odds are s divided by e is not going to be an integer. So where should we look for the best integer?
Closest integer to C.
Anything else?
We're going with the one above and below.
The one above and below. So we just check the first integer to the left and the right. One of them will win. It might not be the closest integer. It could be. It depends. Then you would need to know a little bit more on the graph. So you have 2 options. Option 1, roll up the sleeves, really do some heavy-duty calculus and see what's going on. Or option 2, say, there's only 2 points to check. Let's just check the 2 points. I would be lazy and I would say, let's just check the 2 points rather than trying to find a detailed description of the behavior. There's only 2 things to look at.
It's like linear programming.
It's like linear programming. I was debating whether or not to get into linear programming today because this is such a wonderful topic and it can be done just at the level of algebra of doing lines. Okay. Any other questions or comments about this? Yes?
Tell me, in this C equals S over E, what is it? S belongs
So S is, so originally it was 100,
S is 100.
right. And then we said, exactly. And then we said more generally, we could do 101, we could do pi. It doesn't really matter. The mathematics is going to flow very similarly.
So if we do 100, S is 100, E is 2.17.
Right, so it'd be 100 divided by 2.7.
C is.
Right.
And C tells us,
And that's going to tell us basically where our candidates are for the number of breaks. How many summons do we want? No, the size of each break is going to be S divided by C. And so when we're doing this, we had our function x. We initially had a function of n. And then finding the value of x that maximizes this, x is telling us how many summons do we want. How many pieces? How many pieces? And so we want to have roughly S over E pieces, where each piece is then going to be roughly of size E. And that's going to lead to the largest possible product.
about 32, 33,
Right. Exactly.
2, 3.
Right. But now the difference is, of course, now we have to do integer partitions. And then,
Can we get better if we do?
well, we got to be careful because when we do integer partitions, I can split this up into 33 pieces, but not require all the pieces to be integers. There's levels of complication. So in the 32 3s and the 2 2s, we were assuming not only do we split it up into an integer number of pieces, but each piece is itself an integer. Right now, I'm no longer assuming that each piece is an integer. So if you then add that complication to it, now it's not so clear where the best will be if you have to split it up. But then that one you can just do by brute force. You only have 2s and 3s be to 2s. Okay, other comments on this one? All right, I'm going to hit stop and transfer the file.